Hello everyone, I'm Chloe. Today's session is on data collection sources and pre-processing in environmental science. This module will introduce you to the essential sources and techniques used to gather and clean data for environmental research. By the end of today's lecture, you'll understand how data is collected, prepared, and responsibly used to tackle environmental issues. Let's start with our learning objectives for today. First, you'll learn how to identify and access key environmental data sources, including both public and private datasets. Then, we'll go over techniques for cleaning and pre-processing data, which is essential for ensuring data quality. Finally, we'll discuss the ethical concerns in environmental data science, such as data privacy and bias, and how they impact the integrity of environmental research. Environmental data sources and collection techniques. To begin with, let's talk about the types of environmental data sources. We have two primary categories: public datasets and private datasets. Public datasets are often open-access resources provided by governments, research organizations, and NGOs, and are accessible to anyone. Examples include NASA's satellite data and the European Copernicus program. On the other hand, private datasets are often collected by corporations or research institutions that may require permissions or licenses to access. For example, some agricultural companies collect proprietary data on soil health and weather patterns. Now, let's look at data collection techniques. The main methods include remote sensors and satellites, weather stations, and IoT sensors. Remote sensors and satellites provide large-scale data on atmospheric and surface conditions. Weather stations capture localized data, such as temperature and precipitation, while IoT sensors provide real-time environmental data from urban areas to remote ecosystems.
Each of these techniques plays a crucial role in monitoring our environment. Case study: real-time data access for climate monitoring. A great example of real-time data collection is the work done by NOAA, the National Oceanic and Atmospheric Administration. NOAA uses a combination of satellites and ocean buoys to monitor sea levels, weather patterns, and ocean temperatures. Real-time access to this data is incredibly valuable. In 2020, NOAA tracked a record 30 named storms in the Atlantic hurricane season, providing timely warnings to affected areas and helping communities prepare and respond more effectively. This case study highlights how real-time monitoring can significantly improve disaster response and environmental planning. Data cleaning and pre-processing techniques. Once we have our data, the next step is cleaning and preparing it. There are three main tasks in data cleaning. Handling missing data. Data might have gaps due to equipment failures or sensor malfunctions. We can fill these gaps with methods like interpolation, where missing values are estimated based on surrounding data points. Noise reduction. Environmental data can be noisy, meaning it includes irrelevant or random data. Applying a filter or rolling average can help reduce noise. Outlier detection. Outliers are extreme values that don't align with the rest of the data and can distort analyses if left untreated. Identifying and, in some cases, removing outliers ensures that our dataset remains representative. For example, air quality sensors in a city might report unusually high or low readings due to interference. By cleaning and standardizing this data, we ensure that the resulting analysis truly reflects air quality trends. Practical example: pre-processing air quality data. To bring this to life, let's look at a practical example: pre-processing air quality data. Urban air quality data often has gaps and irregularities due to sensor outages, extreme fluctuations, or urban activity. Here's how we might clean it. Identify missing values. We can use interpolation techniques to fill these gaps. Filter noise. Smoothing techniques, like a rolling average, can help us account for daily variability. Outlier removal. We remove data points that are far outside normal ranges for that location or season. Once cleaned, the air quality data provides a clearer, more reliable picture of urban pollution, which is essential for public health studies and policymaking. Techniques for pre-processing large geospatial data. Geospatial data presents unique challenges due to its size and complexity. Think of all the layers needed to map land use, pollution, or biodiversity across large areas. The main challenges include size. Geospatial datasets are often enormous, especially when they cover large regions at high resolutions. Quality. Data accuracy can vary depending on the source, so standardizing and validating data is critical. To process this data efficiently, we use techniques such as data aggregation, combining data points to reduce the size of the dataset; spatial interpolation, estimating unknown values within a specific area; normalization, ensuring data remains consistent across different geographic boundaries. One powerful tool for this is GDAL, the Geospatial Data Abstraction Library, which enables data conversions and standardizations across various geospatial data formats. Dealing with time series data now, let's move to time series data, which is common in environmental science. Time series data, such as temperature readings over time, requires specialized techniques because each data point is connected to previous and future points. To handle time series data, decomposition, separate the data into trend, seasonal, and residual components, which helps in identifying underlying patterns. Smoothing, this reduces minor fluctuations and reveals broader trends.
Imputation, filling missing values in a way that maintains the data's continuity. For instance, climate models rely on temperature and CO2 levels collected over decades. These techniques help ensure that predictions are based on consistent and accurate patterns. Working with geospatial data and GIS Geographic Information Systems, or GIS, allow us to analyze and visualize geospatial data. GIS is a powerful tool in environmental science as it enables us to map phenomena like deforestation, biodiversity hotspots, and urban heat islands. For example, in wildfire-prone areas, GIS data can show which regions are most at risk, enabling first responders to prioritize certain zones. GIS data layers allow us to assess land use changes over time, helping planners make better environmental decisions. Ethical concerns in environmental data science. Data ethics is critical in environmental science, especially when data affects communities. 3 key ethical issues are data privacy. Data collected in urban areas can sometimes infringe on individual privacy. For instance, certain air quality data may indirectly reveal private information, like location data. Data ownership. Who owns environmental data? Is it the organization that collects it, or should it be publicly accessible? Bias and incomplete data. Missing or biased data can lead to incorrect conclusions and affect policy decisions. A recent example includes air quality data in cities. Areas with fewer monitoring stations, often low-income neighborhoods, may be underrepresented in pollution studies, leading to policy decisions that overlook these communities. Data bias and its impact on environmental models. Bias is a significant challenge in environmental models, and it often stems from how data is collected. Sampling bias. This happens when the data does not accurately represent the whole population. For instance, temperature data collected only in urban areas will miss rural temperature trends.
Measurement bias. Sensor errors or biases in data processing can distort results. The impacts of these biases are substantial. In climate modeling, for example, biased datasets might underestimate risks in the global south, which can lead to uneven support and resources in climate change mitigation. In summary, today we covered data sources, collection techniques, and pre-processing methods. We also explored time series and geospatial data, and finally, discuss the ethical concerns in environmental data science. These foundations are essential for reliable environmental research and responsible data use. Clean, representative data leads to accurate environmental models, which in turn influence policymaking and resource allocation. To conclude, data collection and pre-processing are the building blocks of effective environmental science. Addressing ethical concerns, such as data bias, is crucial to ensure that our models and analyses are fair and accurate. Now, let's open the floor for questions. Feel free to ask about any part of today's lecture, whether it's data sources, pre-processing techniques, or ethical considerations in environmental data science.